We now take a few minutes to look at the idea of dynamic power calculation using some kind of a degradation mechanism as a basis instead of voltage limits. So if you refer back to the previous chapter, we remember that the goals of this dynamic power calculation are as follows. We want to compute a discharge power limit based on the present battery back conditions to estimate what is the maximum discharge power that might be maintained for the next time horizon of delta t seconds without violating preset design limits on cell voltage, SOC, maximum design power, or current, except now we are going to replace that cell voltage idea with something else. And same for charge power, we are going to replace that cell voltage with something else. What we're going to do is to look for the maximum charge or discharge current that the cell can withstand and then convert that value to power by multiplying by voltage. But unlike before, degradation mechanisms are the key. They are the limiting factor, not the cell terminal voltage limits. In this section, I'm going to talk about an idea, and this idea is not thoroughly tested. It's barely tested, I think you could say, at this point in time. But it's an idea that I hope will spark some imagination and lead to efficient ways of computing dynamic power limits that could be used in a real application. It's closely related to a control system design methodology that's called model predictive control. Model predictive control is a big subject area. We have a whole course on it, ECE5720, I believe, on how to do this in general terms. But the basic idea is not terribly hard to understand. At every point in time where I have a decision to make as to what the input to my system should be, for us it's the input current, we are going to find an n-length sequence of control signals where n is looking into the future. There's some time horizon in the future where I'm finding what should be the current right now, and the next one, and the next one, and the next one, and the next one, and so forth. And using a model of the system, we predict what is the performance of that system for that n-length sequence of control signals. And then we find these control signals in such a way that we have the controlled variables converging towards some desired values. And then we, instead of implementing all of those n things and then repeating, we implement only the first of those n things and then repeat. So in a timeline, I determine this is the signal of future, but I implement that one. And then the next point in time, I determine a slightly different trajectory because conditions have changed, because of disturbance or who knows what, and I implement only that one. And the next time I figure that's the future thing to do, but I implement only that one. So the fact that I'm predicting n samples into the future gives actually some robustness to the method, because especially because what we're going to consider are some hard constraints that I cannot violate. These hard constraints. Well, if I don't look into the future long enough, I may not realize that I'm coming close to a constraint, and then because of the momentum of the system dynamics, I may actually exceed that constraint because there's no other thing I can do if I don't look into the future long enough. So model predictive control looks into the future, allows me to see a hard constraint coming and then to gently come up against that constraint without exceeding it. So for us, we might be interested in predicting some constant current input that would not violate some design limits on this cell, and would optimize some cost function that could involve degradation if we applied it for the full delta t seconds, but we're only going to implement one of these at a time. Now, the method, I don't say it here, I don't think, but the most important part of model predictive control versus other types of control is that built into the methodology is the ability to handle hard constraints. The thou shalt nots, thou shalt not cause lithium plating to happen, thou shalt not cause lithium depletion to happen in different places of the cell. Things like that can be implemented very naturally using model predictive control, whereas other types of controls can only do soft constraints by basically approximating a constraint with a quadratic cost function or something like that. So this is one reason why we're looking at model predictive control in this example. The standard model predictive control that you would learn in 5590 is a little different from what we look at here. We're going to simplify the model predictive control here because we don't need all of the complexities of the method. So I'll say right up front some of the changes that we're making. Model predictive control reformulates the system model. So instead of having UK, or the current, as the model input, we change the model so that a change in current is the input to the model, so a delta of that. And that makes sense in a lot of control scenarios. It doesn't necessarily make sense in the battery scenario where we're trying to predict maximum power limits, so I'm not going to do that here. What the delta U input does is it adds an integrator to the dynamics, and that's excellent for control as long as you do it right, because it eliminates steady state error even if your model is a little bit wrong. But we don't need that integrator for power estimation, and in fact it might make power estimation more difficult because it makes the problem less stable if you do it wrong, especially. It also the delta U is used for set point control of some, I want to control a chemical process, so I want to have it so that I have a nice, beautiful, homogeneous output chemical, and that's my set point, and that would occur when I'm in steady state and my delta U's are 0, and that's wonderful. But for us, we don't have a steady state in the battery power estimation problem, so that's not too important for us either. And finally, the standard model predictive control does not allow the state space model to have a direct feed-through term, a D term, and that we need because in our voltage equation we have, for example, minus R0 times current, which here is going to be UK, and that's a direct feed-through term. And even if we don't use a circuit model, if we use an electrochemical model, and I want to see what's happening to, for example, phi s minus phi e, that's a critical variable for determining degradation, that has a D term, it has a direct feed-through term, and I need to be able to implement that. So part of what we're going to do here is to do something like model predictive control in many ways, but not exactly the same as model predictive control, that allows us to have this D term and to use UK as the input instead of delta UK, and so forth. The optimization we're going to come up with is going to be a constrained nonlinear optimization. However, it has a form that's not quite as general as nonlinear programming. It's a little bit more specific. It's called a quadratic form, and that allows us to use a quadratic optimization procedure, which is much faster than just a general nonlinear optimization. This is also used by model predictive control, by the way, so MPC uses faster optimization than fmincon, and we'll see how to do that. We are going to assume for the time being, well, for this section, a completely linear dynamic system model, so that the new state is equal to an A matrix times old state plus B times input, and output equals C times state plus D times input. And of course, our battery cell model is nonlinear, so if we want to apply this to a battery problem, you might say, oh, wait, that's not good, that's not going to be good. But in fact, it's going to be okay, because we can use the linearized outputs of the battery. If you remember that, we had the tilde outputs, And as long as we can cast our constraints on degradation into these linearized variables instead of the nonlinear variables, then I can use this directly. And even if I can't, because I'm doing a prediction over a relatively short time horizon of capital N samples, I can probably linearize the nonlinear dynamics using Taylor series expansion to come up with a model that is linear and accurate enough for the next N samples in order to be able to perform MPC-like optimizations. So it's okay, I think, to have a linear system model even when we know that there are nonlinearities involved. So yk here are some performance variables that we would like to control to some limit or to maintain with some hard constraints. So we might want to maintain phi s minus phi e to prohibit lithium plating. And you go back to the equation for overpotential for lithium plating and you decide what that threshold must be. So we can do that. Or we might like to have state of charge controlled to some maximum state of charge. So I can put state of charge in one of these linear outputs. If I don't need some output, maybe I don't need CSE for some reason, well, don't put it in Y. These are performance variables. These are not necessarily the entire exhaustive list of variables that we might want to have for computing cell voltage and other things. So this yk may be different from the normal system outputs that we've called yk in the past. We are going to predict these performance variables n samples in the future. So we're going to define this vector capital Y has yk and k plus 1 all the way up to k plus n. And it's a column vector, but I've written it as a row vector transpose to save some room. And uk are all assembled into a big U vector of all of the future control inputs. And when we do this and we go through the equations on the previous page, we know that y at time k is equal to c times x at time k plus d times u at time k. That one we know. But if we want to do yk plus 1 equals c times xk plus 1 plus d times uk plus 1. And then we substitute in xk plus 1 is a times xk plus b times uk. Then we're going to get c times a times xk plus c times b times uk plus d times uk plus 1. And that's what we have. We have yk plus 1 is c times a times xk plus c times b times uk plus d times uk plus 1. And we keep on doing that to predict all of the future variables, performance variables of interest up until time k plus n to get an expression for all of these y's in terms of all of the u's. And there's two matrices that are automatically formed when we do this. This matrix, C, Ca, Ca squared, Ca cubed, all the way up to Ca to the nth power, we're going to call that F here. We've seen this before, by the way, back in the previous course. We called that the extended observability matrix. We have a slightly different name for it here. We call it F. And then we have this matrix where on the diagonals we have D, and then I've got C times B, then C times A times B, etc. This is a Toeplitz matrix, and we've seen that before in the same setting, I believe, way back in the previous course when we unwrapped these equations. But overall, we can write Y, capital Y, equals capital F times the present state plus this phi matrix times U, the future inputs. So future performance outputs, a function of present state and future inputs using known matrices F and phi. now we define a cost function that we wish to optimize, and it will be subject to some constraints. And I don't put the constraints here, I just put the cost function itself. And I don't actually explain it especially well, so let's spend a moment looking at it. RS is the desired final value for y. You could think of it as a desired trajectory here. It's a vector the same size as y. So if we want some performance variable like, for example, state of charge maybe, if we wanted state of charge to follow some trajectory, then RS is that future trajectory of state of charge versus time. If we had, well, yeah, we'll just leave it at that. So RS minus Y is our failure to achieve that trajectory. If we can't, if for some reason the optimization produces a set of Y versus time that's different from RS versus time, then there is a tracking error between the desired trajectory and the achieved trajectory. And we put this in a quadratic form, so it's RS minus Y transpose times a weighting matrix. So this is some positive definite weighting matrix Q. Could be just some diagonal that says we care more about some trajectory elements than other trajectory elements. So maybe we care more about the final element than any of the others, for example, is possible. And also all of this part of the cost function is weighting our failure to achieve the desired trajectory. And then here we have a different weighting on the magnitude of the control input. So U is the size of current. So U transpose U is the sum of the squares of the currents. And I can put this other weighting matrix R in there. So Q and R are kind of complementary weights on the failure to achieve a desired trajectory versus the control effort, the amount of current per unit time required to get there. And these are design optimized, well, they're tuning factors in the design. So if we build a design for one set of Q and R, it will do one thing. If we build a control algorithm for a different set of Q and R, it will do something else. And we can adjust these and decide what we like. In fact, I think with standard model predictive control, it's not possible to set R to 0, but if I remember correctly, the method that we've developed here, it is actually possible to set R to 0. So if we don't care about the size of the current, except that it has to satisfy some constraints, then we can completely eliminate that term and have a tracking term only. Okay, so that is our cost function that we're choosing to optimize. And then through a series of algebra, we say, well, y is fx plus phi u, so I put that in there, and that in there, and I didn't change anything else. And then we multiply everything out. It's a bit of a mess, but we multiply everything out, and if I've done it correctly, we get all of this. When we are considering this, remember that J is a cost. We've defined it in such a way that it's just a number, it's a scalar. So if this side of the equation is a scalar, the other side of the equation must be a scalar also. And I'm adding together a whole bunch of things. They have to have the same dimension, so it turns out they're all scalars. So that means that a scalar is equal to its own transpose, and that can help simplify. So RQR shows up there. I've got RQFX. Well, there's an RQFX. There's one of them there. But somewhere around here, let's see if we can find it. Yep, RQFX, that is the transpose, and so that is the second one right there. I just transposed it. It's the same thing. And then I've got an XFQFX. That is there. And I've got an XFQ phi u. There's an XFQ phi u there. That's one of them. And here is the other one transposed, so that's the 2. And what else? I've got an RQ phi u here, which is one of these. And then I've got its transpose, RQ phi u all transposed there. That's the second one of those. And then I've got this term here, which is u times something times u there. And then finally that one there. So all of the terms are accounted for in this condensed version of the equation. And I want to optimize J. I want to minimize J by selecting the control inputs U that do it. I point out that this first line, I've organized the equation in such a way that the first line is not a function of U in any way. So that means that J will in general not be minimizable to 0 because there's this minimum limit on how good I can do just based on the dynamics of the system. So I don't even need to worry about this when I'm optimizing. It's a constant that I can't do anything about. So when I'm optimizing, I can choose to optimize this part instead versus U, and I'll get the same result. A different cost, but the same U. If I need to know the cost, then I need to recompute that part and add it in. But if all I care about is the U that minimizes the cost, I can use the simpler version. And looking at the simpler version, I've got some matrix times U plus U times some matrix times U again. So we're going to define some things. This first matrix we're calling H. So no, we're not. H is 2 times that. And then this here we're calling F. So we can write then that the cost that we're trying to optimize, J, is a half U transpose HU plus F transpose U plus some constant. Now, why the half? Well, it's when I take derivatives and solve. If I wanted to do that, then I'm going to basically get a 2 out of this because it's like U squared that cancels the half, so it's just tradition to write it that way. You don't have to write it that way, but it's tradition to do it that way. Okay, so this is the cost function. I have a way of computing H because I know the present state of the system. Oh, in fact, I don't need that for H, but I know the phi, the Q, the phi, and the R, so I can compute H. For X, F, I know X and F and Q and phi, etc. So I know that, and everything else is just U, so I can attempt to find U that minimizes that cost. Again, model predictive control is unique among control methodologies in that it allows us to put hard constraints on some of the control variables. So we do that here. We say y min is less than y max, and y was fx plus phi u. And we can rearrange this to write the y max condition as looking at this, saying that phi times u is less than or equal to y max minus fx, and then looking at the other side, that minus phi u is less than or equal to fx minus y min. And we can combine both of those in a matrix inequality. This should look kind of similar to what we did in the previous section for the fast charging. So I have some matrix times u is less than or equal to some known constant matrix, or overall A inequality times u is less than or equal to B inequality. So at this point, we've defined the matrix H and F and A inequality and B inequality such that we have a quadratic programming problem, which is a special kind of nonlinear programming that has a simpler solution where I can find U star that optimizes 1/2 U transpose HU plus F transpose U such that these inequality constraints are met, and MATLAB has a built-in quadprog.m, quadratic programming, routine in the optimization toolbox that allows us to find solutions to this kind of a problem. So that sets it all up. We would have to come up with desired constraints on the controlled variables and to test it out with different models and see what happens. But this is setting up the idea. If we're looking at predicting power n samples into the future, we could say, let's suppose I've got constant current, like was said before, so I could define U to be a matrix transpose times a scalar, which turns this whole thing, if you go through all the math, into a single variable optimization on U. So we can predict n time samples into the future based on a constant current to optimize the maximum discharge and charge current values that would apply at all times. Again, for the fast charge, the reference RS value for the SOC state would be, if I'm charging, would be to set the SOC to 1, and we'll try to approach 1 as quickly as possible. Or for discharging power, we would set the reference to 0, and we would try to approach 0 as quickly as possible. Now, we could put constraints on this, right? So we could put constraints on SOC that it never went below 10% and above 90% or something like that. So these are just things that I'm trying to get to, but I can't violate the constraints that I put on the variables in here. So I would add some SOC design constraints into that equation also. I want to define other reference variables for soft constraints, such as SEI growth is not a hard constraint. It's not that phi s minus phi e never exceeds this lithium plating boundary of some voltage, but I don't want to get close to the SEI growth boundary of, I think it was 0.4 volts in the example we looked at earlier, so we would have to think about how to add that. And then we would set hard constraints to prohibit lithium plating and lithium depletion and different things like that. So this is an idea only. I wanted to give you a picture for, voltage is not the end of the story here. Cell terminal voltage is not the real reason for why we need power limits. In fact, it's degradation. But I didn't want to leave you thinking, well, there's no way to solve the degradation issue. There is. We have to come up with models of the most important and most severe degradation mechanisms. We have to explore these optimization procedures. And there's a lot of work that can be done to optimize how that's done and so forth. But in principle, all this is quite doable. It's just a matter of a fair amount of future research to get to that point. So I try to end every chapter with a where from here. And we've reached the very end of the course. So the where from here is not something we're going to talk about in this course. It's something that is really future research and something that I hope to include in a third course someday, although probably no time very soon. This is the edge of what is known in battery management. Yes, research groups are working on different ways of pushing that boundary, and I haven't been able to talk about everything that everyone's doing, but roughly speaking, this is where the field is at this point in time. And there's a lot of work to do. So how do we efficiently implement some of these controls? And because these nonlinear optimizations, while they give you great results, they are kind of inefficient, or they're slow anyway. And there's ways of doing that using table lookups, for example, of pre-computed solutions, or who knows what you're going to find out when you do your research in this area. How do we tune these algorithms for different aging mechanisms and different cost trade-offs? All of these things for computing power limits. There's a lot of work that could be done there. Just how do I get the model in the first place, this physics-based model? We have to be able to perform system identification to get the right parameter values. And that's something that's really not well understood right now. And we have some students working in that area, and we hope to have some results from that very soon. How do we model new degradation mechanisms that haven't been modeled before? Again, there's the component that I think should be done by the material scientists and the electrochemists, but there's the component that needs to be done by the controls engineer to reduce the order of the model and to have high fidelity approximations. how do we implement those in embedded systems, and probably thousands of things that haven't even been thought of yet. So over the course of the battery modeling topics and the battery controls topics, I hope your imagination has really been excited and that you have some ideas to explore, and that over time you can help in making the battery management systems of the future even better. So thank you for your interest and your attention in this course. This is a topic that is extremely fascinating to me. I hope that you have been able to gain some enthusiasm in the area as well. And whatever you do in the future, I wish you very, very well.